तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We have been considering about equivalence relation. An equivalence relation is a binary relation which is reflexive, symmetric and transitive. Reflexive, symmetric and transitive. A binary relation R on a set A, if it satisfies these three conditions, it is called an equivalence relation. And we have seen some examples of equivalence relation. One is the mod k, set of integers, take the set of integers and the relation mod k. That is, two integers a and b are related if a minus b is equal to some n times k, or a and b leave the same remainder when divided by the integer k. This is called mod k relation, and we have seen that it is an equivalence relation because it satisfies the three properties reflexive, symmetric and transitive. And it divides the set of integers into k equivalence classes. The set S0 is integers leaving remainder 0 when divided by k, when divided by k. S1 is the integers leaving remainder 1 when divided by k. S2 is the set of integers leaving remainder 2 when divided by k, and Sk minus 1 is the set of integers leaving remainder k minus 1 when divided by k. And we find that none of these, each, if you take any two of them, they are disjoint. There is no element which is present in both of them. These are called equivalence classes of the equivalence relation, and we find that here there are k equivalence classes S0, S1 up to Sk minus 1, and each class is separate from the other, that is, the classes are all disjoint, and the union of them will make the whole set I. The union of all these equivalence classes will make the whole set I, and that is what we learnt in this theorem. Let R be an equivalence relation on a set A, then for all A B belonging to A, either the equivalence class of A is the same as the equivalence class of B, or equivalence class of A and equivalence class of B are disjoint. That is what we meant by equivalence class of A intersection equivalence class of B is phi, they are disjoint. And the union of all such equivalent classes make the whole set A, that is given by the second part. From this we immediately get this result. Let R1 and R2 be equivalence relations on a set A, then R1 is equal to R2 if and only if R1 and R2 have the same set of equivalence classes. Suppose I have a set A say consisting of say A, B, C, D, E, F. Then I have equivalence relation on this. Equivalence relation, you know, that is represented by complete digraphs. So, suppose I have this C, D, E, F. I have this equivalence relation R1 on A represented like this. Now, suppose I want to, this divides A into equivalence classes, A and B be in one equivalence class, C and D in one equivalence class, and E and F in another equivalence class. Suppose I define another equivalence relation R2. If it is divides A, B, C, D, E, F into different equivalence classes, this is E, different equivalence. Suppose I have say A, B, C in one class and D, E in one class and F in one class. If I draw the diagram, there will be a complete diagram with A, B, C, there will be a complete diagram with D and E, and there will be a complete diagram with F. They are different. This is not the same as this. And when will R2 be equal to R1? Only when you have the same diagram for R2 also, same diagram as this, then only the relations are the same. And in this case, A and B will be in one equivalence class, C and D will be in one equivalence class, E and B, F will be in one equivalence class. So, R1 and R2 divide A into the same equivalence classes. R2 also will give the same equivalence classes. Only in that case, you can say that R1 and R2 are equivalent. So, that is what is meant by this. R1 is equal to R2 if and only if R1 and R2 have the same set of equivalence classes. This as an example I have explained. This is true for any set and any equivalence relations R1 and R2 on A. Now, what do you mean by the intersection of an equivalence relations R1 and R2? We know that a relation is essentially a set. It is a set of ordered pairs. A binary relation is a set of ordered pairs defined on a set A cross A. So, you define R1 and you define R2 as a set intersection. You can define R1 intersection R2. So, R1 is an equivalence relation on A, R2 is an equivalence relation on A, and what can you say about R1 intersection R2? This is also an equivalence relation on A, equivalence relation. Let us take as an example the previous one. This is R1, this is R1. The set A is A, B, C, D, E, F, and the set consists of 6 elements A, B, C, D, E, F, and R1 is a equivalence relation defined like this. Let R2 be defined like this: A, B, C, D, then E, F. So, how many equivalence classes you have here? You have A in one equivalence class, B and C in one equivalence class, D in one equivalence class, E and F in one equivalence class. Now, what can you say about R1 intersection R2? It will have all the arcs which are present both in R1 and R2. So, you will find that E, F, these arcs are present in both. So, they are present in the intersection, but the self loops are present in both the relation R1 and R2. So, they are present here, but the arcs between A and B are present in R1, but they are not present in R2. So, they will not be present in the intersection. Similarly, the arcs between C and D are the ordered pair C, D, D, C. They are present in R1, but they are not present in R2. So, they will not be present in the intersection. Similarly, BC, CB, the ordered pairs BC, CB are present in R2, but not in R1. So, they will not be present here. Now, look at this relation. Is this an equivalence relation? This is an equivalence relation because it is reflexive, it is symmetric, and it is transitive. So, how can you say that it is reflexive? It is symmetric and it is transitive. Now, take R1 and R2, both will have the self loops, because R1 is reflexive, both are equivalence relation. Please remember that R1 and R2 are equivalence relation on the set A. So, both are reflexive. So, the self loops will be present in both the thing. So, in the intersection also they will be present. So, reflexive property is okay, reflexive. What about symmetry property? If you have an arc in one direction, you should also have an arc in the other direction. If such a thing is present in R1 and such a thing is present in R2, it will be present in R1 intersection R2 also. For example, here between E and F, such an arc is present, such a pair of arcs are present, that will be present in the intersection also. But if it is present in R1 and if it is not present in R2, or if it is present in R2 and not present in R1, then it will not be present in the intersection. Symmetric means between any two pair of nodes, either there should be no arcs, or if you have one arc in one direction, you should also have an arc in the other direction. So, that condition will also be satisfied. So, symmetry property is also satisfied. What about transitivity? Now, if you have AB and BC in R1 and in R2 also. So, if you have AB and BC in R1 and you also have AB and BC in R2, then it will be present in R1 intersection R2. So, but in R1 is an equivalence relation, so it is transitive. So, AC will be present in R1. Similarly, because AB and BC are present in R2 and R2 is transitive, this will be present in R2 also. So, such an arc will be present in R1 intersection R2. So, the transitive property is also satisfied, transitivity. Since all these properties are satisfied, R1 intersection R2 is an equivalence relation. So, this is an equivalent. For example, we have considered R1 like this, then R2 like this on the set A having 6 elements. R1 intersection R2 consists of these elements. The equivalence classes here are A will be in one equivalence class, B alone will be in one equivalence class, C alone will be in one equivalence class, D will be in one equivalence class, E and F will be in one equivalence classes. These are the equivalence classes corresponding to R1 intersection R2. But we cannot say like this for the union. Suppose R1 is an equivalence relation and R2 is an equivalence relation. Can you say R1 union R2 is an equivalence relation? We cannot say that. R1 union R2 need not be an equivalence relation. And R1 an equivalence relation on ABCD defined like this. ABCD by the digraph like this. Here AB and are in one equivalence class, CD are in one equivalence class. Let R2 be an equivalence relation defined like this. Here A is one equivalence class, B and C are in one equivalence class, D is in one equivalence class. Now, what can you say about R1 union R2? R1 union R2 will have all the arcs present in this or this. It will have self loops at all nodes. It will have this because it is in R1. it will have this because it is in R2, it will have this because it is in R1. This is R1 union R2. The reflexive property is not affected, R1 union R2 will be still reflexive. The symmetric property is also not affected, R1 union R2 is still symmetric, but R1 union R2 is not transitive. You have an arc from A to B and you have an arc from B to C, but you do not have an arc from A to C. That is, you have the ordered pair AB, you also have the ordered pair BC, but you do not have the ordered pair AC, is not present. So, this is not transitive. So, this is not an equivalence relation, not an equivalence relation. But if you take the transitive closure of that, that will be an equivalence relation. Only the transitive property gets affected. So, if you take the transitive closure, you will get an equivalence relation. Let R be a binary relation on a set A and take first the reflexive, then the symmetric, then the transitive closure of R, then the resulting relation is an equivalence relation. R dash is the transitive symmetric reflexive closure of R, then R dash is an equivalence relation on A called the equivalence relation induced by R, and R2 dash, if R2 dash is an equivalence relation and if R2 dash contains R, then R2 dash contains R dash. Thus, R dash is the smallest equivalence relation which contains R. So, for example, take this, take a set A with two elements A and B, like this. This is not reflexive because you are not having a element. It is not symmetric also. Take R. Now, first take the reflexive closure of that. That will be adding a self loop here. Then take the symmetric closure, that is you will be adding the other one. Obviously, it is transitive, so while taking the transitive closure, you do not have any problem, will be the same as this, that will give you an equivalence relation. So, when you first take the reflexive closure, the reflexive property is satisfied, and then when you take the symmetric closure, you get the symmetric property, but the reflexive property will not be affected by that. Then when you take the transitive closure, the reflexive and the symmetric property will be retained, and you also additionally get the transitive closure. Now, if you take any other relation R2 dash containing equivalence relation R2 dash containing R, it will also contain this. So, if I suppose I take some other, here we have taken only two elements, suppose I take some more elements, suppose I have 4 elements A, B, C, D and something like this, R is this, A, B, C, D. Then when I take the reflexive, symmetric and then transitive closure, you get the equivalence relation A, B, C, D, I will add one more element E. Is like this, E I will have this. Suppose I have an equivalence relation R on a set with 5 elements like this. Then when I take the transitive symmetric reflexive closure of R, I get this. Consider relation R2 where you have A, B, E and C, D. This is an equivalence relation because it has got it is represented by a directed graph which has got components which are complete diagrams. Here there are 3 equivalence classes, AB is in one equivalence class, CD is in one equivalence class, E is in one equivalence class. Here there are 2 equivalence classes, A, B, E are in one equivalence class, CD is in one equivalence class. Now you can very easily see that R2 contains this contains this, R2 obviously R2 contains R is present here also. So R2 will contain this. If an equivalence relation contains this, it will also contain the symmetric. This is the smallest equivalence relation containing R. This is another equivalence relation which contains R. You see AB is present there, this self loop is present there, CD is present there. So this also contains R, but it is a bigger equivalence relation. It will always contains the transitive symmetric reflexive closure of R, which is the smallest equivalence relation containing R. That is what this result says. Now we shall see the correspondence between partitions and equivalence relation. What is a partition? Okay. Before going into the formal definition, take some example. Let me have a set A having elements A, B, C, D, E, F, G, H. Then I divide the elements into block. Suppose I can put A, B in one block, C, D, E in one block, F and G in one block, H in one block. Like that we can put. The 8 elements are divided into 4 blocks. You are dividing the 8 elements into blocks, that is called a partition. This is a finite set. If you take the infinite set of examples of integers, you can divide them into 3 blocks having negative integers in one block, positive integers in one block, 0 in one block. So you can divide like that into 3 blocks. Or if you take the set of non-negative integers, then you can divide them into 2 blocks, one having the even integers, even non-negative integers, and another having even odd non-negative integers. You can divide it into, you can partition into odd and even numbers. That is, you can divide it so that into blocks, so that one element is present in only one block and it will not be present in 2 blocks, but every element will be present in one block. So a partition pi of a non-empty set A is a collection of non-empty subsets of A such that for all S belonging to pi and T belonging to pi, either S is equal to T or S intersection T is equal to pi, A is equal to union of S belongs to pi, S is union of S belonging to pi, S is A. That is, you are putting the elements of a set A into blocks and separate blocks are disjoint and one element will belong to one and only one block. An element of a partition is called a block. If pi is a finite set, then the rank of pi is the number of blocks of pi. For example, the rank of this is number of blocks 1, 2, 3, 4, there are 4 blocks. So, the rank is 4 or the index is 4, you can use the word index also for this. Here the rank is 4, which is the number of blocks, or is, you can also say the index is 4. If phi is a partition, then the rank may on a infinite set. Say for example, the set of non-negative integers, you are dividing it into odd and even integers. Okay. So, the rank is 2. There are 2 equivalence class or 2 blocks in the partition, I should say. There are 2 blocks in the partition, and so the rank is 2. But you may also have infinite number of blocks. You can put every non-negative integer in one block. In that case, the rank will be infinite, number of blocks will be infinite. So, if you take the set of non-negative integers 0, 1, 2, 3 up to this, each one you can put in one block like that, then the rank is infinite, rank is infinite. If you put all the odd, all the even in one block, all the odd integers in one block, we are having only 2 blocks, then you say that the rank here is 2. But if it is a finite set, obviously the rank has to be finite only. Now, we see the correspondence between the equivalence relation and the partition. Let A be a non-empty set and R an equivalence relation on A. Then the collection of the equivalence classes AR, collection of the equivalence classes AR, A belongs to A, of equivalence classes under R is a partition of A. In all these examples we have seen that. Again take this example. The underlying set here is A, B, C, D. The equivalence relation R is represented like this. So, the equivalence classes are A and B will belong to one equivalence class, C and D will belong to one equivalence class. Actually, this corresponds to a partition where A and B will be in one block and C and D will be in one block. So, this equivalence relation induces a partition on A, that is this partition, A and B in one block, C and D in one block. Each equivalence class will be one block. So, you say that an equivalence relation induces a partition on A. This is what we have seen. Let R be an equivalence relation over a non-empty set A. The quotient set AR is the partition. This is called the quotient set. This is called A modulo R, the partition of A induced by R. Now, immediately you can see, let R1 and R2 be the equivalence relation on a non-empty set A. Then we have seen that R1 is equal to R2 only if they have the same set of equivalence classes, is not it? We have seen this result earlier. R1 and R2 be equivalence relations on a set A. R1 is equal to R2 if and only if R1 and R2 have the same set of equivalence classes. This we have already seen. So, if R1 and R2 are equivalence relation and R1 is equal to R2, they have the same set of equivalence relation. So, they will induce the same partition on the underlying set. A by R1 is equal to A by R2 means they will induce the same partition, or the underlying set will be divided into equivalence classes in the same way in both cases, that is the same partition is induced in both cases. That is what is meant by this result. So, we have seen that an equivalence relation induces a partition on the underlying set. Conversely, you can have a partition and the partition can induce an equivalence relation on a set A. The idea is very similar. So, look at this set. You are having a set A having 8 elements and there is a partition of that. There are 4 blocks, A, B belong to one block, C, D, E belong to one block, F, G belongs to one block and H alone belongs to one block. This induces an equivalence relation on the set A, where A and B will be equivalent. So, you have A, B, the equivalence relation can be represented by this digraph. F and G are equivalent. So, you will have like this. C, D, E are equivalent. And H alone is one equivalence class. Okay. So, this partition induces this equivalence relation on the set A, and formally if we define this, you say A is related to B if A and B belong to the same block. Formal notation, it is defined like this. Let pi be a partition of the non-empty set A and define the binary relation equivalent, this relation on A as follows. A is related to B is equivalent to saying that there is a block S such that S is a block and of pi and A and B belong to the same block. This is an equivalence relation because reflexive property will be satisfied, A will be related to A because it is in the same block, and if A and B are in the same block, B and A are in the same block. So, symmetric property will be satisfied. Okay. If when you say A and B are in the same block, B and A are in the same block. Then transitive property is also satisfied because if A and B are in one block and B and C are in one block, that is A, B, C, all of them will be in the same block. So, that A and C will be in the same block. So, the transitive property is also satisfied. So, since this relation satisfies all the 3 properties, reflexive, symmetric and transitive, you find that this is an equivalence relation. And you call this equivalence relation as the equivalence relation induced on A by the partition pi. So, this is called an equivalence relation on A called the equivalence relation induced on A by the partition pi. So, we see that an equivalence relation induces a partition on the set A and a partition on the set A induces an equivalence relation on A. Let pi be a partition of a set A and R an equivalence relation over A. Then pi induces R if and only if R induces pi. Obviously, that is true. Look at this. This is the set A. This is a partition pi and this is the equivalence relation R. Pi induces this equivalence relation R and you can see that R induces this partition on A, this partition pi on A. So, pi induces R if and only if R induces pi. So, this is the correspondence between equivalence relations and partitions. Next we shall see what is meant by a refinement of a partition and also what is meant by product of two partitions and sum of two partitions. Let pi and pi dash be partitions on a non-empty set A. Then pi dash refines pi if every block of pi dash is contained in a block of pi. We say pi dash is a refinement of pi or pi is refined by pi dash. If pi dash refines pi and pi dash is not equal to pi, then pi dash is said to be a proper refinement of pi. Now, let us see what is meant by that. Take an example. A is the set, say A, B, C, D, E, F. Then pi is a partition on A where say A, B are in one block, C, D, E, F are in one block. Pi dash is another partition where A, B is in one block, C, D is in one block, E, F is in one block. Now, look at pi and pi dash. There are 3 blocks here, there are 2 blocks here. Every block of pi dash is contained in a block of pi. This is contained here, this is contained here, this is also contained here. If this condition is satisfied, you say that pi dash is a refinement of pi or pi is refined by pi dash. That is, in essence, what is meant by pi and pi dash? Pi and pi dash are partitions of A and pi dash refines pi, then we can think of the elements of pi dash as having been obtained by breaking up the elements of pi into smaller subsets of A. So, here this is broken up into smaller elements. So, you are dividing into 2 parts. So, you are breaking it up. So, this is called the refinement of R and pi is said to be refined by pi dash. Of course, pi is its own refinement. If they are not equal, one is called the proper refinement of the other. Pi dash is a proper refinement of pi. Now, obviously, a partition induces a equivalence relation. So, pi will induce an equivalence relation on A, pi dash will also induce an equivalence relation on A. What is the connection between these two equivalence relations? Let us see that. Let pi and pi dash be partitions of a non-empty set A, and let R and R dash be the equivalence relations induced by pi and pi dash respectively. Then pi dash refines pi if and only if R dash is contained in R. Obviously, see here, pi induces an equivalence relation where A, B are connected by, it is a complete digraph, and C, D, E, F are connected in all possible manners. Okay, I will not draw it completely. Whereas pi dash, you will have A, B like this, but this, okay, this is R, R is induced by pi. I will draw this C, D, E, F. And all pairs of arcs are present. This is the equivalence relation represented by a digraph R which is induced by pi. Now, pi dash also induces an equivalence relation. It will not have all these pairs, but it will have these elements, right. Pi dash induces R dash which will have these elements. Obviously, whatever is present in R dash is present is in R also. So, R dash will be contained in R. So, you can very easily see that pi dash refines pi even only if R dash contains R. R dash is contained in R. Let C be a collection of the partitions of a non-empty set A, then the relation refines is a partial order over the elements of the set C. Again, I will take just 3 elements in a set A and see, let us see what are the partitions. Take a set A having 3 elements A, B, C. What are the partitions? Pi 1 is a partition having all the 3 elements. Pi 2 is a partition having each one in a separate block. Pi 3 will be a partition having A and B in one block and C in a separate block. Pi 4 will be A in one block, B and C in one block. Pi 5 will be A and C in one block, B in one block. Now, which one refines this? See, pi 2 will refine this, this, this and this. Pi 2 will refine every one of that. And pi 3 will refine this, pi 4 will refine this, pi 5 will refine this. This is breaking this like this. But none of pi 3 will refine pi 4 or pi 5. Pi 4 will not refine pi 3, it is not breaking up like that. So, this will induce a partial order like this. Pi 2 will be the lowest one or the least element, you can say. Pi 3, pi 4 and pi 5, and pi 1 is refined by everything. So, this is a partial order, it is a Poset diagram or a Hasse diagram. Pi 2 refines pi 3, pi 2 refines pi 4, pi 2 refines pi 5, and by transitivity pi 2 refines pi 1. Pi 3, pi 4, pi 5 refine pi 1, but pi 3 and pi 4 there is no connection, pi 4 and pi 5 there is no connection, and so on. So, it is represented by a partial order like this. Next, we shall see what is meant by the product of two partitions. Let pi 1 and pi 2 be partitions of a non-empty set A. The product of pi 1 and pi 2 denoted by pi 1 dot pi 2 is a partition pi of A such that pi refines both pi 1 and pi 2. If pi dash refines both pi 1 and pi 2, then pi dash refines pi. So, let us see what is meant by the product of a partition. Let A, B, C, D a set, this is a set, and pi a partition like this, A, B in one block, C, D, E in one block and F in one block. This is pi 1. Pi 2 is A, B in one block, C, D in one block, E, F in one block. Okay. This is an example. What do you mean by the product of pi 1 and pi 2? Pi 1 we have represented like this, sometimes you represent like this, the product of pi 1 and pi 2. What is this? This is a partition pi such that pi should refine both pi 1 and pi 2, and any other partition which refines both pi 1 and pi 2 should refine pi also. So, it is obtained like this. So, consider this in this example. AB is a block here, AB is also a block. So, that will be retained as it is. Now, CD is one block, C and D are in the same block here. So, CD again will be a block here, but EF is in one block here, E and F are in different blocks here. So, you cannot have EF in one block, E will be in a separate block, F will be in a separate block here. You have to split it. CDE will be split as CD and E, and EF here will be split as E and F. Now, you see that this one refines pi 1, okay. Each block is contained in a block of this. This also refines pi 2. So, you see that pi refines both pi 1 and pi 2, and if you take say pi dash equal to say A, B, C, D, E, F, this is some other partition. You see that pi dash refines pi 1 and pi dash also refines pi 2. You see that pi dash also refines pi. So, that is the condition. The product of two partitions pi 1 and pi 2, which is denoted as pi, refines both pi 1 and pi 2, and if pi dash refines both pi 1 and pi 2, then pi dash refines pi. Now, what is the connection between this and the equivalence classes represented by them? Let R1 and R2 be the equivalence relations induced by the partitions pi 1 and pi 2 of a non-empty set A. Then the relation R is equal to R1 intersection R2 induces a product partition pi of pi 1 and pi 2. So, if this induces an equivalence relation, that equivalence relation will have three components. What are the components here? Corresponding to pi 1, if you have R1, R1 will have AB, the equivalence relation can be represented like this, then CDE, and F. R2 will be represented by AB, CD, EF, and pi induces R, that will be AB, CD, and E and F. You can see that the intersection of these two is this. See, this is present here, this is present here, it is present here, and CD, this is present here, this is also present here, it is present here. The other elements which are not present in this are removed, and you have a self loop at E and F. So, the intersection of R1, R2 is R, which is the equivalence relation induced by the product of pi 1 and pi 2, induced by pi. Now, we will see what is meant by the sum of two partitions. Let pi 1 and pi 2 be partitions of a non-empty set A, then the sum of pi 1 and pi 2 denoted by pi 1 plus pi 2 is a partition pi such that both pi 1 and pi 2 refine pi. If pi dash is a partition of A such that both pi 1 and pi 2 refine pi dash, then pi refines pi dash. Say, take the same example here. A is a set like this, pi 1 and pi 2 are partitions like this. The sum of these two pi 1 pi 2 is a partition pi such that both pi 1 and pi 2 will refine pi. So, here AB is a block here, AB is a block here. So, that will be in one block. CD is in one block here, but CD is in block which also contains E. So, you have to include that also here, and here E and F are in the same block. So, you have to include that also here. So, this is the sum of pi 1 and pi 2. AB will be in one block and CD, EF will be in another block. Now, you see that pi 1 refines this, pi 2 also refines this. If I take another one, say the whole set A, B, C, D, E, F in one block, pi 1 and pi 2 refine this, but you note that pi also refine this. So, if there is another partition which is refined by pi 1 and pi 2, it will be refined by the sum also. Okay. So, that is a definition of this. And what is the connection between these equivalence relations? Let R1 and R2 be the equivalence relation on a non-empty set A induced by the partitions pi 1 and pi 2. Now, we have seen that R1 and R2 are equivalence relations, but R1 union R2 need not be an equivalence relation. Now, pi 1 will induce an equivalence relation R1, pi 2 will induce an equivalence relation R2. We have seen what is that in this example. R1 is this, R2 is this. Now, pi induces another equivalence relation, but you see that R1 union R2 need not be an equivalence relation, but what is the equivalence relation induced by pi? That is R, and that is in this case it will be A, B and C, D, E, F in one block, that is C, D, E, F, and the self loops all over like this. This is the equivalence relation R induced by pi, and it is the transitive closure of R1 union R2. If you take the transitive closure of R1 union R2, that is the equivalence relation induced by the sum partition R1 union R2 plus equal to T of R1 union R2. Then R is an equivalence relation on A, and the partition A bar is the sum of pi 1 and pi 2. Now, if you have two partitions pi 1 and pi 2, the sum is unique. You cannot have two different sums. Why? If I have say pi dash as the sum of pi 1, I have two partitions, say I have two partitions pi 1 and pi 2. The sum of pi 1 and pi 2 is unique, Why? If I have two of them, say pi of two sums, say pi dash and pi 2 dash, this will refine this by definition, and this will refine this. That means pi dash is equal to pi. You cannot have two different sums, they will be equal. And similarly, the product of two partitions, if you have two partitions pi 1 and pi 2, the product of the partition is denoted by this. You can have only one product. If pi dash and pi 2 dash are two products like that, pi dash will refine pi 2 dash and pi 2 dash will refine pi dash by the definition, and so they will be equal. So, the product is also unique. Product is unique. So, we have seen the relation, equivalence relation in detail. This has got a lot of application in several fields of computer science, and we have also seen the connection between partitions and equivalence relations, and what is meant by the product of partitions, sum of partitions, and how they induce new equivalence relations on the underlying set.